So here's the short story of it. Imagine you have 2 points. We'll call this point P 0 and this one P sub n. And you've got some curve connecting them that maybe looks like, I don't know, do something totally silly like that. Now, we want to find the length of this curve between P0 and P sub n. Something we couldn't do before. We could find lengths of line segments, right? Remind me, how did that work when you found the length of just a line segment like this? Let's pretend. Hold on, let me catch up with you. I like that you guys are jumping in. Let's call this x sub I and then call this x sub I minus 1. And then this would be y. Hold on, do I want to? Yes, I do want to use that notation. Y sub I minus 1, and this is y sub I. So how did you find this distance d?
Very pretty much you gotta thank Pythagoras for that one.
That's true. You do have to thank Pythagoras for that one. Can we be more specific? What are we using to find
Pythagorean theorem.
the Pythagorean theorem? True. What, there was another name that you give it to it when you're dealing with a distance? That would be the slope. That would be the result you would get if you made. This is an interesting conversation. I'm enjoying this. Go on.
No,
I already gave you a huge hint. I gave you most of the name of it already.
I hear it.
If I repeat it, then you'll know what I'm talking about. Distance formula? Is that what I heard? Distance formula. Do we remember the distance formula? Okay, I'm hearing yeses and nos. So let's use what our teen was talking about as far as Pythagorean theorem. Look at my little triangle there, my right triangle, yes? The distance horizontally here, is that x sub I minus x sub I minus 1? Is that the distance from here to here? Because that's the same as the distance from there to there? Yes? You with me? Yeah? Ryan, you with me? Because you look kind of checked out. You with me? All right. All right. How about the distance here? How am I going to write that? That's the same as the distance here, right? So y sub I minus y sub I minus 1. And then I was told to use the Pythagorean theorem. So you're telling me that we have the light blue squared minus the green squared, right? A squared plus b plus, thank you. A squared plus b squared equals d squared. Yeah? Oh, and just take the square root on both sides, and now you have the distance formula? No? Is that not the distance formula?
The hardest is gonna get in calculus.
Oh, God, no. It's going to get way harder than this. Is that okay? Okay. So there's our distance formula. So we know how to find the distance between 2 points along a line segment. Yes? Okay. So how does that help us here? Well, what we're going to do is we're going to create a bunch of points on here. That'll be P1, P2. We'll pretend they're equidistant apart on the floor there. P3, and then just keep at. I'm not going to label them all. We'll just keep going like that. Okay. And then maybe we'll choose this one right here to be P sub I minus 1, and this one here to be P sub I. And directly under that, we've got the value x sub I minus 1, and over here, x sub I. Okay. Now, could I approximate just the part of the curve between P sub I minus 1 and P sub I? Could I approximate that distance with a line segment? I could use the distance formula to find that red distance, correct? The one that we just derived up above. Yeah? Okay, what would that look like? Well, wait, wouldn't it just look like, whoops, Wouldn't it just look like this? Isn't that exactly what we just derived up above? Yeah. Yeah. So that's the distance formula for the line segment between what this part means is basically the absolute values are saying, give me the distance between P sub I minus one and P sub I. Good. Does it make sense to use absolute values for distance?
Yeah, yes.
Why?
This can't be negative.
Okay, I like that, but there's another reason to think about it.
Just period.
Absolute value of -3 is +3 because that's the distance from the origin. So absolute value basically is distance. Yes? Okay. Anyway, so that's why they've used that notation. So we're good with what's in the red box. It represents the length of what?
Line set.
The line segment from where to where? P sub I minus one to PI. Yes? P sub I. Okay, good. Whoops. All right. So that's helpful. Now, do you agree that that this is a change in X and this is a change in Y? Okay. Totally good. This is just the distance formula. Now, you guys hanging in there? Yeah? Yeah, for sure. Never see these two faces or this. Okay, are we good? All right. Now, we need to eventually integrate, but as you know, we are only allowed in this class to integrate with respect to one variable only. Either it's dx or dy, usually it could be du or something else, but it's only one variable. But here, this distance formula has two variables. It's got x's and y's, right? So our goal now is to get rid of one of the variables. We're going to get rid of y using something you learned last semester. Okay, so check this out. It's not as bad as it may at first appear. If you remember back from last semester, I'm gonna zoom way in on this guy here, this little bit here. I'm gonna zoom in, and it looks something like kind of exaggerated, maybe like this. And I've got this guy right there. Okay. Let's see. You guys did something where you took the slope of that red line, which is y sub I minus y sub I minus 1 over x sub I minus x sub I minus 1, right? That's the slope of that secant line, if you will. And then you started thinking about the derivative of this function. And you guys did the mean value theorem. Do you remember what that said? There's a whole bunch of, you know what, let me get my fancy tangent line here. So that's tangent to the blue curve, yes? At this point right here where my dot is. And I've got all these different tangent lines as my points travel along the blue curve. Are we in agreement? Must be, one of them must be what? Parallel to the red line. That's what the mean value theorem says. It says somewhere in here, there's a point so that the slope of the tangent line at that point is equal to the slope of the secant line. That's what the mean value theorem said. Hopefully you remember it. So if that's the function f in blue, there has to exist somewhere between x sub I minus 1 and x sub I, what we're going to call x sub I star, some x value in that interval number I, such that the derivative at x sub I star has to equal the slope of the secant line. That is mean value theorem. Cool? Vague memories of this? I have no idea how in depth you guys did this. Yes.
I thought the mean value theorem was when there's like there's an intersect. I think it rules
Rolle's theorem actually was some, if you have your endpoints are the same, somewhere in between there has to be a zero slope tangent line. So maybe you're thinking of the intermediate value theorem? Okay, yeah. But this is definitely mean value theorem. I didn't make this up. I promise. So if we take this box and then multiply both sides by the denominator here, all of a sudden it looks just like this, does it not? The only difference is instead of y sub I and y sub I minus 1, it's f of those x values. I should have paid attention to that and I didn't, but there it is. So that is mean value theorem. And if we change this to delta y, this green part here can get shoved in there, which is what you see, whoops, yeah, which is what you see right there. And the whole point of doing that was so now we have a function, a distance function for x only. You with me? Yeah, maybe, yes? Okay, so simplifying this down, you can factor out the delta x's squared, take them out of the root, and now we're here. Now, that only gives us one line segment. So what do we have to do? We have to come up here and we've got to take this line segment, that line segment, that line segment, this one here, and just keep going. And what are you going to do with all these little line segments? You're going to, well, before you do that, you have to add them all up, right? So you're going to add up all those line segments, which is what you're, or lengths of line segments, which is what you're seeing down here. And then we want, do you agree that the more line segments, the closer we get to the actual length of the curve? You guys want to see a visual for that? I don't know, this might be a waste of time. Do you want to see a little visual? Yes, no?
Sure.
Sure? Okay. It's not, I don't know. I like this sort of stuff. I think it's kind of neat to look at. I didn't save it. I need to go over here and grab it from here. But I know exactly where it is, so it's this one. So it should be pretty quick. Okay, so we're basically looking at finding the length of that blue curve. Hold on, let me make sure that this is being shared. Video as well. Here, let me just do this. Okay, so we want to find the length of that green curve, right? And if you just did one length using the distance formula, that is a very bad approximation for the length of the green curve. How do you get a better approximation? Switch it to, I don't know, 4 lengths, right? You can find each one of those line segments, lengths, add them up. You have a much better approximation than when you were back here. Agreed? But what if you want something even better? What are you going to do with the number of line segments? Get more and more and more of them, right? There's 30 line segments there. It looks like they totally disappeared. But if you zoom in, you'll see, if this will let me zoom in, it's still not exact, is it? But if you zoom out, it's awfully close to what we are really looking for. So what do we have to do with the number of line segments? 30 is not enough. We've got to send the number of line segments to infinity. Cooper?
That monster equation on the bottom, we have to solve.
So no, because when we take the limit of a Riemann sum, right? This is a Riemann sum, or well, yeah, this is summing each one of those, right? We're going to take the limit as the number of them goes to infinity, and we're just going to get an integral. So, visual, did that help? Was it worth the time? I don't know. This is one of those things that, for me, it's this sort of idea is what kind of captivated me when it came to math. I had no interest in math when I was in high school. I took pre-calculus in high school when I was a senior, and I hated it. I barely passed with a C. And then I ended up taking calculus years later. And when I saw this sort of thing, it was really Riemann sums back when we were getting areas under curves. It blew my mind for whatever reason, and I couldn't stop doing math since. So I don't know. If you're sitting there going, I don't like math, I get it. I've been there. But if you want to be an engineer, you got to learn to like math, because engineering is just applied math. So the only reason I say that is I've had a lot of students over the years at IVC, come to me and say, I want to be an engineer, but I hate math. And I tell them to seriously consider changing their majors. Seriously, I mean, you don't want to spend your life doing something you hate, right? I don't know. That's my opinion. I don't know. Maybe your parents have a different opinion. All right. Are we good? Question.
Can you talk,
Absolutely.
can you explain where we got the delta y equals f prime x sub I star?
That right there?
Yeah.
So this is not erasing for some reason. One moment, please. This tablet is on its last legs, I think. This right here was mean value theorem, correct?
Yes.
This is, I had y sub I here and y minus y sub I minus 1. They're just using it with function notation. Yes. And so this right here is delta x. This right here is delta y.
Oh, I see.
That's all. And then once we have that, we replace this in here to get that.
Okay.
Cool. All right. So here's the story. Arc length, generally speaking, is not something that people come to me and go, oh gosh, I can't understand how to do this. It's super hard. What happens with most calculus students is they memorize those two formulas, which are virtually identical, except for one is when you have a function of x versus a function of y. The issue comes with the algebra needed to rewrite the integral to be able to integrate it. Okay, so we're about to do two examples. The setup on either example is not super hard. You're just gonna take the function, find its derivative, plug it into that formula, and put in the limits of integration. But then you're gonna have this integrand, right? The thing you're taking the integral of is gonna have square root with a big old mess, and you're gonna have to manipulate it in order to get it to a point where you can actually do the integral. That's the hard part. It's all algebraic with a little bit of calculus at the end. So, in example one, Alex, will you please read it out loud for us? Thank you. Now, Alex, is this a function of x or a function of y? Function, y equals x, it's y equals f of x, right? Where f of x is the x to the 2/3. So that's a function of x, yeah? Does that make sense? Okay, so that means we're living up here. Cool? Is that good?
Function of x.
Yes? So what do we need to get this done? Jaden, when you look inside here, you notice we need the what? Okay, good. So if f of x is equal to x to the 2/3, what's f prime of x, Jaden? Okay. Morgan, does his derivative look correct? Okay, good. Katali, did they give us limits of integration here? Okay, good. So I am taking that circled formula up there. We're integrating from 1 to 8. We have the square root of 1 plus 2/3 x to the negative 1/3 squared dx. Oliver, am I looking good so far? Yeah, Juan, we're good? Okay. Ryan, why? Any ideas on what we might do? First of all, integrating this immediately is absurd. Yeah. You're not going to use sub that. It's a horror show. So, Ryan, why? Any ideas on what you might do to start simplifying this thing? Okay. So when we square the inside of those brackets, we get 4/9, and then we have x to the, Matthew, we have to multiply the exponents. Is that right? So we get negative 2/3. Sana, are we in good shape? Okay. All right. Now, I could just tell you what's next, but I want to hear from the group. What do you guys think we should try? This is still not going to be fun to integrate. Ryan G. Okay. What next? Anybody? It's okay to not totally see what's gonna happen. This is, again, this is what makes this tricky. Once we get our integral into the proper format, it's gonna be something we know how to do. It's gotta be, otherwise we can't do it. So what should we try next? He had some, but there's some over there. Kleenex?
I'm.
Oh, I don't know, what to tell you. It's not my room. All right. Talk to me. So you got to be a little careful with that. If I were to give you the square root of 25 plus 16, that would look like this, which if you were to tell me that that equaled 5 plus 4, which would be distributing the half exponent being 9, this inside here does not equal the square root of 81, right? So we're not actually allowed to do that. That's a no-no. Okay, but it's good to have the conversation now as opposed to after I grade your exam. So I appreciate you bringing that up because you're not the first person to have thought about that. What's another thing we might be able to do to simplify what's in there inside? Yeah. Okay, so you're talking about making a common denominator, is that right? Now, wait a second, is there more in the denominator than just the 9? Oh, there's also the x, so let's go ahead and rewrite that this way. Let's go ahead and put 1 plus 4 over 9x to the 2/3 to the half power dx. Is that looking okay? And then, as Ryan alluded to, let's go ahead and make a common denominator. So we have 9x to the 2/3 over 9x to the 2/3. Yeah? Still good? A lot of times with stuff like this, you're not just going to look at a problem and immediately know how it shakes out and how it turns into something you can integrate. You just have to start simplifying and simplifying and simplifying until you get someplace. Do we now have 9x to the 2/3 plus 4 over 9x to the 2/3 all to the half power? Yeah. Okay. Now what? Still looks like a horror show. Some of you might be thinking it actually looks uglier. And it depends on how you look at it, right? Beauty is in the eye of the beholder. Oh, okay. So you're saying you want to have the integral from 1 to 8, 9x to the 2/3 plus 4 to the 1/2 over, can I just change the bottom to 3x to the 1/3? Basically take the square root of the top and the square root of the bottom separately? Are we seeing it? Or did I skip a step that's not making people happy? I don't know. I'm still learning.
The square root of the bottom.
Right. What we have here, if I can erase something on the previous step, it's the same as the square root on top and the square root on the bottom, right? That you are allowed to do, right? If I gave you the square root of, I don't know, 36 over 9, that's the same as 6 over 3, which is 2, or also known as the square root of 4, right? So you're allowed to take the square root on top and bottom for sure. Okay, does that help us? What can we do now to simplify this? Excellent. Take the 1/3 out. And then I'm going to do something that maybe will kind of grease the wheels to the end of this problem. Can I write this? Why do you think I wrote it that way? That's correct. Okay. Now, everybody's algebra is in a different place. I'm barely aware of where you guys are at with your comfort level with this stuff because you weren't my students last semester. But this is the sort of thing that makes these sorts of problems difficult is how do I manipulate what's in the integrand so I can actually integrate this thing? And the only way I know to get good at anything in math is experience and tons of thoughtful practice. That's it. I don't know, there's no magic bullet for this stuff. So, we're gonna let you be what?
9x to the 2/3.
And du, when I multiply the 2/3 in front, am I getting a 6x to the negative 1/3 dx? Which gives us 1/6 du equals x to the negative 1/3 dx. Are we happy with that x to the negative 1/3 dx? We absolutely are. I'm going to go over here. So we have 1/3 times 1/6. I'll deal with the limits of integration in a moment. Du and back. I'm going to have u to the half power. Is everything taken care of? Here's my u. Here's my du. Everything except for the limits of integration is good. Whoops. Freaking computer. Okay, so we have to change the limits of integration. Here we go. I like to do this in red because this is where a lot of mistakes happen. When x equals 8, u is equal to 9 times 8 to the 2/3 plus 4. When x is equal to 1, u is equal to 9 times 1 to the who cares plus 4. So we're changing limits of integration here. 8 to the 2/3. Are we comfortable with doing that in our heads? Cube root of 8 is 2 squared is 4. 4 times 9 is 36. 36 plus 4 is 40. And then down here, I think we'll get a 13. Okay, horrible limits of integration, but there they are. 13 to 40. Good news is the rest of this is relatively straightforward. We're doing okay? Okay, so we've got 1/18 u to the 3/2 with a 2/3 in front. Double check your antiderivative before you move on. Did I get it right? Yes, no, maybe? I don't know. Or I do know, but I want you to know. Right? If you take the derivative of u to the 3/2 with the 2/3 in front, does it take us back to there? This right here, does it take us back to there when we take a derivative?
Yeah.
Okay. And now we're down to this thing. You see where the 1/27 came from? If I skip a step and something doesn't make sense, I need to know. I'll happily slow down and do it. But if I don't know, I'm just assuming you guys are good.
Question.
Yes, sir.
What if we use the power of 3/2? So we need
If you take the derivative of this, you should get that. Good?
not the 1/18.
Well, the 1/18, this guy right here is sitting out there. Yeah?
Yep.
Okay. So I see students run to their calculators with this 40 to the 3/2. I'd rather you do this. Isn't 40 to the 3rd taking 40 times itself 3 times? And then the half power is a square root. So it's really 40 times 40 times 40 under a root, which can be rewritten as 40 root 40, right? Because these two come out, minus 13 root 13. Is that cool? And then, of course, the square root of 40 can simplify even further. So we get 1/27. I think I can take a 4 out, which becomes a 2 times 40, and we're left with a 10 like that. Okay, so I'm doing a lot of this algebra, simple algebra arithmetic kind of fast. But that's just because we've got bigger, more important things to deal with. Let me make this so it fits here. All right. How are we doing out there?
How did you get that down to
We're gonna have
40?
space
40?
about 5
You gotta
minutes.
get-
Say again?
We're gonna have space about 5 minutes.
Yeah, I know. I've been told I need to allow more space. Okay. The question, Artine, was how did I get 40 root 40? So if you look here, let me get rid of some of my colors here. Is that cool? Did he explain it well enough?
Yeah.
Okay, good. All right, so again, the calculus on that was not bad, was it? The calculus was setting up the integral, which was relatively straightforward, just plugging in a derivative into the square of blah, blah, blah. And then the calculus, once you got it to here wasn't bad because it was just a calc 1u sub. But all the algebra in between was really the issue. And the exact same dynamic is going to happen on the next example. So find the length of this curve. Do you guys need to see this anymore? Do we pretty much have it? Yeah. Yeah. All right. So I want to see if you guys can do this setup on your own. All I'm going to say is let's write our function. First of all, is this a function of X or Y? It's a function of Y. So I'm going to call it G of Y. And let's rewrite it so we can take a derivative really easily. How should I rewrite this function so it's easy to take a derivative? Say again, I didn't hear you. Okay, so I would start off by putting 1/10 y to the 5th, and then you're saying 1/6 y to the -3, and then you can just use the power rule. Yeah? Okay, so go ahead and find g prime of y, and then go ahead and set up your arc length as you see at the top of the screen there, which is L equals the integral from 1 to 2, 1 plus, or here, I'll do it this way. Okay, take a derivative, plug it in there and start simplifying. And if you need to talk to each other, just start seeing how these things come together.
That makes no sense. You saw pretty much same groups, so break down the 5 guys. So then 1 have y to the 4th. So, and then 1/2.
Okay, so all that was spot on. You're not taking that.
1 plus 1 is 1 minus 1. No, you're not putting it in. So G prime 1.
Am I trying? Do you have the same thing?
G prime 1. No, let's bring up 1.
Try something.
Wait, y 4th.
How we doing over here, gentlemen?
Y 4th. Minus y to the 4th. Minus 1 over 5. So y 4th minus y to the y negative. Y to the negative. So now it's plugged in. So minus y to the negative.
Looks like you two have.
So now let's plug it in. Here's the on track. Here's what it says.
Plus brackets.
So now let's plug it in. 1 plus 1/2 squared. Y 4 minus y to the 12.
Or.
So when you multiply.
Oh, that's all squared.
Okay, so you're saying square this out?
Oh, yeah, then you have to.
Yeah,
We're not done.
yeah,
That's all right. Well, just
no, not just set up, keep going.
Oh,
Yeah. that's where you have to talk to each other, figure out how you're gonna
Wait, then what if?
deal with,
Make a one into a two or two one.
actually, I need to do this on the story.
I mean, oh yeah, I guess you do that.
It's pointless. I was thinking that. It's kind of pointless when it is.
Oh,
Look,
wait.
these all have Ys with them. These all have Ys. So why? You wanna square the inside? Oh, it's all in the square root.
Is that what you did?
No, because you have to square.
You gotta be careful in multiplying it up, but that's exactly what you wanna do.
Um,
All right, so I'm gonna steal from a group that's working on this. Here, let me catch up with where you guys are at. So are we getting a 1/2 y to the fourth minus 1/2 y to the negative fourth? Is that what we all got? So then we're going 1 to 2. We've got 1 plus 1/2 y to the fourth minus 1/2 y to the negative fourth squared like that. Did I, first, I just want to make sure, is everybody up to there? Sana and Josh, we're in good shape up to there? Cooper and Matthew? Yeah? Okay, so, this crowd over here is saying we can take the 1/2 out. You can, I'm wondering if it's easier not to. I haven't tried it that way, maybe later on I can write it up. What Morgan and Kutali and company started doing is they started squaring this out. Does that seem like a reasonable way to go? Yeah. Now, let's go off to the side and make sure we square this correctly because it can get squared incorrectly very easily. If I write this out twice and multiply, whoops, that's not what that says. When we multiply here, what are we getting? I heard 1/4 y to the eighth. We're adding exponents, correct? Okay. What happens when we multiply here? First of all, are we going to get a positive or a negative? Negative 4th y to the what when you add exponents? 0. Are we all seeing that? Okay, I'll come back to that just one in a moment. Multiplying here, do you get the exact same thing? And then multiplying in back, you get now a positive 1/4 y to the negative 8. Okay, so we've got 1/4 y to the 8th minus a fourth, right? We were told by Cooper and company that y to the 0 is 1, correct? So we can combine those to get negative a half. Is that a reasonable step there? Morgan, are you cool with that? You might have had that on your paper. I didn't really see it very carefully. And Morgan, you're okay with the exponents? Okay, cool. So at this point, you might be saying, this does not look any better. If anything, it looks worse because I've got bigger exponents. And I wouldn't totally disagree with you, but watch what's about to happen. So, are we good so far? Before you tell me what's about to happen, I just want to point something out here. From where we started to where we ended, we multiplied to get from here to here, correct? Does that mean you should be able to factor to get from here to here? Yes. Okay. Now, I don't know about you guys, but most algebra classes don't ask their students to factor something like this. Did your algebra teacher at any point expect you to factor something like that? Okay. You're in calculus now. You're going to be expected to factor something like that. Okay. Now, what's going to happen? Here, actually, before you tell me what's going to happen, let me write it in here in black. 1 to 2, we have the square root of 1 plus 1/4 y to the 8th minus a half plus 1/4 y to the negative 8 dy. Just a second, Cooper. I just copied what's in the green box and replaced the part that's being squared. Cooper, what were you going to say?
Take that beginning one, subtract the 1/2, and then do backward.
Okay. Did you guys hear what Cooper said? Nobody's responding. Nobody even heard you. So we're going to combine the blue, right? I'm going to put this in front. I'm going to put now what? The blue combines to what?
One.
What kind of 1/2? A positive 1/2. And then we're going to have this 1/4 y to the -8 and back. And all that is under the root. So that's a -8. I don't know if you can see that. Okay. How we doing? Yeah. And so then Cooper said, let's go ahead and factor this. Is it going to be similar to how that factors? Very similar. Yes?
Yeah.
You think so, but you're not sure. Okay, let's try it out. Oh, is that believable? If we come back to here real quick, if I put a plus sign here and a plus sign here, I'd get a plus sign here, a plus sign here, and a plus sign there. Yeah? So that means that this thing here with the plus sign factors to 1/2 y to the 4th plus 1/2 y to the -4th quantity squared under a root dy like that. I know, algebra gets ratcheted up. Ryan Y, ask a question.
What you did, literally just,
I factored.
so what we have inside right now is the end result of when we simplified, and then you just did that process essentially backwards.
I'm not sure what you mean.
Like
Yeah,
on
but,
the-
we multiplied combined like terms and then got a result that we then factored. Do you want me to show the factoring in more detail?
Yeah.
Yes? One moment, unless it's something to clarify what I'm about to talk about.
No, I see that. Like, show how we would-
Yes, I'm going to show you that right now.
Can I go
Okay,
down?
so there's the inside of the square root, yes?
Yep.
Okay. We want to try to factor this. Give me two same things that multiply to this. 1/2 y to the 4th, 1/2 y to the 4th. Agreed? Give me two same things that multiply to this. 1/2 y to the -4, 1/2 y to the -4. Yeah? So we agree that that product gives us the first term and that product gives us the last term. Yes? And if you were to multiply these in the middle, do you see a 1/4 y to the 0 power? That's 1/4 y to the 0 power. And out here, when you multiply those, you get another 1/4 y to the 0 power. Well, slow down. But do you agree with those? What he said. They both need to be positive so that these now add up to 1/2, correct? Artine, you see it?
Yeah.
So if those add up to 1/2, I need a positive here and a positive there. So that's the full story on how to factor it. Now, everybody learned their method of factoring differently. Did you guys do like the box method or the X method or all these varieties? Okay, I don't care for those methods. I kind of just do a trial and error method, I guess. But whatever works. Are we okay with the factoring? Now, I'm spending a lot of time on this is because this sort of factoring is going to come up again. You're going to see this in homework problems. You're going to see this perhaps in a video assignment. You might even see it on a quiz or a test. This comes back. It comes back in future classes, future math classes as well. So we are now here. Why is this a good place to be? Before we think about u sub, the square and the square root undo each other, and we're left with this. We don't need to u sub at all. We can just add 1 to the exponent and put a 1/10 in front, right? if you want, but I didn't, and I want to keep going, so, is that cool? Did I do that right? Take a derivative of what I have. Tell me if I'm correct. I don't trust myself. I need another coffee. Is that correct? The derivative of 1/10 y to the fifth is 1/2 y to the fourth? All right, you guys losing steam? Are we losing steam already? You guys have a whole day ahead of you, don't you? Yeah, but for the rest of the day, you don't have just somebody barking at you the whole time, right? You guys work in groups, you do activities, right?
Oh.
No, you get barked at all day? Oh, it must be more IVC classes then, huh?
We're good, Barkley.
What do you guys have next? Chemistry? Is that with Mrs. Chang?
Say we have essay writing after this, and then we have things.
Essay writing?
Gonna be barking and drilling all day.
Okay, I'm ending up there when I plug in the 2 and the 1. I think we've been at this problem long enough. Let me just tell you what the answer is. And I got an ugly number, 779 over 240. Generally speaking, as you'll see once we take our first exam, I normally don't give you exam problems that have horrible number answers like this. Sometimes, but usually not. So the reason I do that is I'm not trying to test you on your ability to type things into a calculator or do arithmetic. I'm testing you on your ability to set up an integral and be able to evaluate the integral. So oftentimes the integrals on exams are not going to be horrible, scary number experiences. However, you will be expected to do all the different sorts of setups that we've seen. How are we doing out there? Yeah? How are we doing on time? That, yeah,
Oh, this is long.
I don't know if I'd call that a long problem. We spent most of our time doing algebra, right? As far as the calculus problem, I don't think that's a very long problem. We'll have longer, I promise. It might not have as much algebra, but all right. Where does that put us? That puts us down here. Let's I'm going to go through this this derivation a little on the quicker side, I think. Just kind of get the concept across, and then we'll jump into doing a couple more examples. Hopefully you can finish this section today, talk about what you have working on this weekend, and then you'll be set. We'll finish up. So our goal now is we're going back now to surfaces of revolution, but we're not talking about solids anymore. We're talking about just a surface, and we want to find a surface area of revolution. Okay, so imagine like we just do one that looked like this, if I remember correctly, something like this. Didn't we do something like that along the x-axis? And we did it as a disk method and as a shell method. Yeah. Are we good? Yeah. So imagine now, instead of a solid, right? Instead of rotating the solid region between these two or under this curve, we're just rotating the curve itself. And now we're just getting a shell, if you will, and we want that surface area. Okay. To get there, here's what we're going to do. We're going to imagine that we have some horizontal axis, and we're going to spin around this axis, but all we're going to spin is a line segment like that. And I'm going to call that L, have length L, this line segment. And I'm going to call the distance here little r1, and I'm going to call the distance there. Actually, I'm going to back that off a little bit. The distance there, big R2. And the reason I'm calling them that is because when I rotate this guy around, it's going to give me a it's going to give me a surface that looks something like this. A what? A funnel? I was thinking a lampshade. Anyway, this is called a frustrum of a cone. And it's basically if you take a right circular cone and cut off the tip, it looks like this. Okay, so that's what this is called. Now, I'm not going to talk too much about where the derivation of this comes from, but this right here, I'll just say a couple things. This right here is the area of a frustrum. Okay. Now, L is that blue length. 2 pi r sure feels like a circumference, correct? Let me just finish this off and then I want you to think of that r, that radius, as being the average radius right here, meaning this right here, the average of R1 and R2. And so 2 pi r ends up being the average circumference across this frustrum. And if we multiply it by the length L, we end up with the surface area of this guy. In other words, we end up with this yellow surface area. So, Cooper, what was your question? Forgot it? Think about it. Oh, yeah.
Would this not be the same as just taking the line segment, like the previous question, we were trying to find the length of the line? Or length of the curve, and then just throwing that into the disk method, but that's.
The problem with that is that's giving you volume. Disk method is a volume thing. Here, that red circle, it's not a solid disk. It's just a circle with an emptiness within it. That sounded really weird the way I said that, but an emptiness within it. It's sad that way. All right, are we in good shape with the, again, I didn't really derive the formula in yellow, but that's the basic idea for the surface area of a frustrum. That's, if you wanted to, we could derive this all the way through. I don't know that it's the best use of our time. All we're going to do is this. And again, I'm going to do this a little on the fast side, so hopefully we have time to get through the remaining examples before the end of class. But if I were to take a curve now between A and B, I want you to imagine maybe a curve that looks like this. And I rotated that about the horizontal axis. I would get a surface that maybe looks like this. Not perfect, but I think it's probably enough to get the idea across. Yes? You with me? Okay. Now, just like we saw before, if I take a little subinterval, maybe I'm going to make it relatively big, but call that x sub I minus 1 and x sub I, and go straight up there. I've got these 2 points on this curve. I could definitely get this length here, correct? Using distance formula? Yes? And when I twirl around that blue length, maybe I'll call that L, just because it looks familiar to what's above. I'm going to get a little mini frustrum like this. Yeah? You following what I'm getting at?
This in a dishwasher. Something in this.
Dishwasher is a solid. This is just the shell, the outer portion. And we're finding the surface area of the shell. We're not finding the volume. Okay? And so we end up with this yellow band, which is really just a thin frustrum. And I made this way thicker than I normally would. It should be really thin, because guess what? If we can find that surface area on that little band, we can find the surface area on a bunch of other bands, and then we can add them all up. And that's what we're doing when we take, I'm trying to decide how much of this I'm going to say. So let's just say surface area of band is A equals 2 pi. I need this radius, right? You guys remember up above, that red radius right there was R? Tell me about this red radius here. Isn't that just the length up to the function at some x sub I star? And so that radius in red is going to be our f of x sub I star. And then I need L, but wait a second. can't I use the arc length between those 2 points? And we know the arc length between those 2 points to be 1 plus f prime of x sub I star quantity squared, right? This is what we just did earlier in class. That's the arc length between this point that I just made really big and that point that I just made really big. So now we're multiplying our circumference times arc length, and the thickness is delta x. So what we end up with is that's the area of one band. We need to add up a whole bunch of them. I equals 1 to n 2 pi f x sub I star square root of 1 plus f prime x sub I star squared times delta x. And then we take the limit as the number of bands goes to infinity, and we end up with this right here. So that was a very quick kind of run through this. It's the same idea that you saw with area under curve. It's the same idea with our shells and washers and discs and arc length, where we break it up into a bunch of little intervals, find the result approximately on that one interval, and then take a limit as the number and sum them all up, and then take the limit as they go to infinity. That happens over and over and over again in calculus. Yes.
For the revolving around the horizontal and vertical axis, in essence, aren't they just the same equation with the variables?
Right, so let me get to that in just a sec. Are we okay with the basic setup of what I was getting at with the derivation there? Now, all these derivations, we could go into an obscene amount of detail, but we don't have, unfortunately, enough time for that. So what Cooper is noticing is, and this is worth talking about, I was planning on having this conversation. Notice here that we have a function of f of x, and we're revolving about a horizontal axis. This was the example that I kind of just showed you. And when that happens, the radius is this f of x, okay? But if we're going to rotate about a vertical, sorry, I want to change colors there, a vertical axis, it's the exact same thing, but now it's just the value x that's going to be the radius, right? And you can kind of quickly see that. If I give you a function of x that looks like this, and you rotate it around the vertical axis to get something like this, and you're trying to get its radius like this for one of these bands, right? A little band. I made that look too much like a disk. But anyway, that radius is just an x now. Okay, so that's what happens when we're rotating a function of x about each axis, right? So that's a function of x. But now if we have a function of y, we kind of have a similar setup where if we're about the horizontal, it's just going to be y here. And if we're about the vertical, it's going to be g of y. So it's going to take a little bit of paying attention to figure out which one we're doing. That you have to draw it and pay attention. But again, kind of like with the arc length, once you have the setup, it's mostly algebra. Okay. We don't have a lot of time. Let's do one. Let's make sure we at least get one of these examples done, and then maybe we'll do the other one next time. So they want us to find the area of the surface formed by revolving this function about the x-axis between x equals 0 and a half. So your first job is to find f prime of x. Here, let me write first f of x using exponential notation like this. F prime of x. Who wants to tell me what to write? Don't everybody volunteer at once. Chain roll. Give me some chain roll. Who's got this?
1 minus x squared, which makes it to the negative 1/2 times 2x.
Negative 2x.
Oh, it is negative 1.
Excellent. Thank you. And then if we were to simplify that a little bit, do we get a negative x on top and a square root of 1 minus x squared on the bottom? Is that all that reasonable? Yeah? Okay. So now we've got to plug it into this thing. So they're using S for surface area. And because we have a function of x and we're revolving about the horizontal axis, it's going to be similar to the very first one we had there, from a to b, 2 pi, revolving around the horizontal axis. That means the vertical f of x is going to be your radius. So there's your circumference. And then arc length. So one way to memorize this, kind of similar to what we did with disc washer and shell, is we've got circumference times arc length times thickness. So if you like that, go for it. But all right, what do we have? We've got the 2 pi on the outside, integral from 0 to a half. F of x is simply the square root of 1 minus x squared. And then we have the square root of 1 plus the derivative squared, which is going to look like, I'm just going to put it in without skipping steps for a moment. Okay, so there it is in all of its glory. And again, at first, it looks like a horror show. Our hope is to be able to rewrite this in such a way that's going to simplify so we can take a reasonable integral. Any questions on the setup so far? We have a function of x. We rotate about the x-axis. That means that the radius here for our circumference is f of x. How do you guys want to simplify this? Okay, square top and bottom. So we're going to have still the square root of 1 minus x squared. In here, we're going to have 1 plus x squared over 1 minus x squared dx. And then can we rewrite that 1 as 1 minus x squared over 1 minus x squared? Right? This yellow 1 here. Does that look like a 1? No, it doesn't look like a 1? Okay, thank you. That yellow 1 became that. So I made a common denominator. 2 pi integral from 0 to 1/2. Still good? Yes, no, maybe?
Yes.
Okay. We have 1 minus x squared under a root. Here we're going to have, what happens when you add up this green part plus that green part? And you're just, the x squareds cancel and you just get a 1 on top and you have 1 minus x squared on the bottom dx. Now what?
Wait, they cancel.
They cancel. What do you mean? Who cancels?
Does the square root push the numerator and denominator?
So the step I'm not going to write would look like this. Right? Because you can bring the stuff in the square root inside. Okay, so the step that I'm not going to write just becomes this, right? Reasonable? What's the antiderivative of 1? X, and we're evaluating from 0 to 1/2. So our answer is just pi. What the heck did we just do? It's so easy to forget. We just took, the arc length is involved, but we just took, this guy is a circle of radius 1, right? It goes from -1 to 1, and this is the entire, that's basically the function f of x equals the square root of 1 minus x squared, and 1/2 is maybe about here. We just took this green portion of our curve like that, and we rotated it about the x-axis to get a surface that looks like this. Not a solid, right? Right. And we just found that surface area. It just happens to be exactly pi units. Pi square units, I should say. Cool? Yes, no, maybe, yeah? Yeah, question. How did I get from here to here? Wait, really, what you're asking is how did I get from here to here? That's what you're asking, okay? When you have two square roots, when you have the square root of a times the square root of some other number, that's the same as the square root of a times b, agreed? And if that b is 1 over a, then this becomes 1 over a, and they cancel, just give us the square root of 1. Is that all good?